intuitionistic fuzzy vector given by xg is called solution of the intuitionistic fuzzy linear system 1 if it satisfies the following equations. Now, in this section, we define the dual intuitionistic fuzzy linear system and we solve it. Usually, there is no inverse for an intuitionistic fuzzy number. Therefore, therefore, the intuitionistic fuzzy linear system EX equal to BX plus Y cannot be replaced by the intuitionistic fuzzy linear system E minus B X equal to Y. So we define the dual intuitionistic fuzzy linear system as follows. Dual intuitionistic fuzzy linear system is a system of equations where the coefficient matrix A and B are real and the unknown YI and the YI and the unknown XG are intuitionistic fuzzy number. We say that of vector x1, x2, xn given by xg is a solution of the dual intuitionistic fuzzy linear system 2 if it satisfies the following equations. Now, in this part, we will solve the dual intuitionistic fuzzy linear system in special case where EIG and BIG is are positive. Then the dual intuitionistic fuzzy linear system is equivalent to these equations. It follows that we have the following equations, and if A minus B minus 1 exists and has only non-negative entries, the dual intuitionistic fuzzy linear system 2 has a unique intuitionistic fuzzy solution. Therefore, we get this theorem. If A IG and BIG be non-negative matrix, the dual intuitionistic fuzzy linear system 2 has a unique solution if and only if A minus B minus 1 exists and has only non-negative entries. Now we solve the dual intuitionistic fuzzy linear system in the general case. To solve it, we try to replace the dual intuitionistic fuzzy linear system by 4 crisp linear systems. So the dual intuitionistic fuzzy linear system is equivalent to this equation: the first equation, the second, the third, and the fourth, where EIG, FIG, GIG, and HIG are determined as follows. It follows that we have the equations 4, 5, 6, and 7, and hence we get 4 crisp linear systems 8, 9, 10, and 11, where the matrices M and N contains the absolute values of A and B respectively. If A minus B and M minus N are non-singular, then we have xm plus, xd plus, xm minus, and xd minus. Then we get to get a solution for the dual intuitionistic fuzzy linear system, we just take the extremities x plus and x minus, and we have this theorem. If A minus B and M minus R.
Please, you have to respect the time.
Thank you. If A minus B and M minus N are both non-singular, the dual intuitionistic fuzzy linear system has a solution under these conditions. And we take this example to show the applicability. To solve this system, we construct 4 crisp linear systems. Then we have the intuitionistic fuzzy solution x1, x2. So in this presentation, we introduce dual intuitionistic fuzzy linear system, and to solve it, we replace the original dual intuitionistic fuzzy linear system by 4 crisp linear system. And thank you for your attention.
Thank you very much. We come to the questions. If you have some questions. If somebody have a question. Nobody have question? If you have some question. Nobody? We go to the next presentation entitled Approximation of Fuzzy Number by Fuzzy Elements of Fuzzy Algebra by Idris Bakdash and all.
Thank you, sir. Okay, thank you. Firstly, I will share my screen. Yeah, yes, I'm there. I try to show you my screen.
You can share with us your presentation.
Okay, I try it. There's some technical problem. Okay. You see now my screen? Are you there?
Yes.
Yes, we see your screen. Yeah, yes.
Okay. So hello everyone. I would like first of all to thank the organizers of this conference, even if the situation is not easy because of coronavirus. So let me introduce myself. My name is Idris Bakdash. I'm a PhD from University Sultan Al Islam, Faculty of Sciences and Technology. I'm a member of from Laboratory of Applied Mathematics and Computing Sciences. So as you can see on the screen, my topic today is about approximation of a fuzzy number by a fuzzy element of fuzzy algebra. So in this presentation, I will talk firstly about a fuzzy set, and I would like to recall some basic definition and properties that will be needed in the next section. For the section 3, 4 results, and finally I will end by conclusion. So as we have seen previously by Hafida, that the notion of fuzzy set was introduced by Professor Rashid in 1965 as an extension of a classical subset. So since that, many researchers have focused to investigate this theory, especially the notion of fuzzy differential equation. So in this notion, we need the product of fuzzy numbers. So we know that the product of fuzzy numbers is not stable. For that, many attempt to approximate a fuzzy number by a special fuzzy number but triangular fuzzy numbers or trapezoidal fuzzy numbers to preserve the multiplication, but it's not enough. So in our aim is to construct an algebra that we preserve the notion of fuzzy, the product of fuzzy number. So let's recall some definition as we have seen previously by Hafida. A fuzzy number set is defined as follows: is a fuzzy class who satisfy for properties is normal, fuzzy convex, and upper semi-continuous, and the closure is compact. As a remark, we can say that the alpha cut is an interval of the real line, with U alpha is the upper alpha cut and lower alpha cuts. The multiplication by a scalar is defined as follows. We define also the distance between two fuzzy elements by this equality. And we can say the space of a fuzzy number with the distance is a linear normal space with the norm is the distance between the fuzzy element and the zero, the fuzzy zero. And now let two fuzzy elements, we defined the product of fuzzy number, the alpha cut of this product by this equality. And we have now generalized local difference is defined by this property. Is defined by Stefanini and Bidi. In terms of upper level, we have the generalized Fuzzy-Hikuhara difference is defined in terms of alpha. We have also, as you've seen in the screen, the norm between of the generalized Hikuhara difference equal the distance between two fuzzy elements. Now we move to define the generalized Hikuhara derivative, defined also by Stefanini and Bidi. We move to define the differentiability, always by Bidi and Stefanini. We have two cases. Case one, E just differentiable at x0 if the derivative is defined by this equality, or case two, if we have now the upper is change the place with the lower. There is a difference between case one and case two. Now we define the product. The derivative product is defined also by this equality. The integral, the Fuzzy-Riemann integral is defined by these properties. And if f is GH differentiable with no switching point on the interval AB, we have the integral, the fuzzy integral between EB of a fuzzy valued function equal the fuzzy valued function in the point B minus with the minus is GH differentiable is the difference of the fuzzy valued function on the point B. So we move now to our aim. Our aim, firstly, we define what that is mean fuzzy integral. So in this section, consider P the set of R fuzzy number such that this fuzzy number written by this form. So we can show that this set and the class is a group Also, we can show that the product is stable on P, which means that this P is a groupoid under the product and is a group under plus. Now the quadruply P plus the product of fuzzy number and scalar and the product by a scalar is an algebra. For the idea of the proof, first prove the quadruply is a vector space. So we can, it's easy from lemma 1 and 2 that P plus is a group. GH is the inverse of plus and stable by products. And we can show easily that this quantity is true. So P plus, sorry, there is one plus here, is a vector space which imply our results, which imply that the quadruply is an algebra. This algebra named fuzzy algebra. So now to definition, we defined a new kind of distance d2 by this equality, and we can prove that E1, the subset of fuzzy number, and with this new distance is a complete metric space. Now we define the inner product on P by, on our space P algebra by this application. So we can show that P is a convex closed subset of the class of element of fuzzy algebra, of fuzzy number, by respect to the D2 metric space defined previously. For the idea of the proof, we take an element of our algebra. So there exists a subsequence in P such that the distance goes to 0. So we use a property of Breeze's theorem, and we take T in the interval 0, 1 and U in P. As we know, we have this quantity equal minus C alpha and C alpha, where C alpha is the alpha cut. As you see in the screen, we have in this form. So this form show us that our element is in P, which implies that P is a convex subset. Sorry. Go now to the approximation. In this section, we consider the set E1, A defined as this form. We have the subset is stable by product, and for two fuzzy numbers U and nu are approximately, we say it's approximately equal. If we have this property, we have mu x minus u x is less or equal epsilon for all epsilon, and we write u approximately equal mu. So two fuzzy numbers u and mu are of our algebra approximately equal if we have the distance d2 between these two fuzzy elements are less.
Please, you have respect the time.
Okay, sir. So as an important result, we demonstrate that E1 is approximately equal P. So for each element in our set of elements is approximately equal V. So I will go for respect to the time to the application. For application of this method is we find the solution of this equation in the space E1. So for that we move to the algebra B, because the product of two fuzzy number is not defined in E1. We move on to algebra to solve the equation, and we have the solution. And thank you, sir.
You have to respect the time.
Okay, thank you for your attention. Yeah. Thank you.
Thank you very, very much for your speech. Now, if someone have a question. If there is some questions. Anybody has questions? Thank you very much. We get to the next presentation entitled Mathematical Fuzzy Model to Going Up Smoking by Mr. Abdelhati Alawi.
Thank you, Mr. Belaid. Hello, everybody. First of all, I want to thank the ICOA committee for agreeing to present my work entitled Giving Up Smoking from a Mathematical Point of View via Fuzzy Mathematical Model, in a collaboration with my thesis director, Professor Saeed Miliani, and my thesis co-director, Madam Lalla Saadiya Shadli. My presentation is organized as follows. I will start with an introduction, then we'll recall some basic tools used to build our results in a preliminary. Then we will move on to the crisp model and the fuzzy model. The section 5, it's about numerical results. Then we'll finish by a conclusion. So our basic model is the following system of nonlinear differential equations, where L is occasional smokers, P potential smokers, Q temporary quitters, R smokers who quit permanently, and S AV smokers, which means who smoke 20 or more cigarettes per day, and so on for the other parameters. So we recall here some tools. We define what we mean by a fuzzy set. So it's a subset of a classical set defined on universe X, and it's defined by a mapping defined on X a value into 0, 1, called membership function, or a degree of membership. So as you see here, so this is a classical set characterized by the characteristic function, a value into the kappa 0, 1, and here we have a fuzzy set, and it's characterized by a function, a value into 0, 1. So if we take each element here, so it has a degree of membership between 0 and 1, and so it's characterized by a function into the interval 0, 1 called membership function. So it's a generalization of the characteristic function. So we can see that a classical set is a particular case of a fuzzy set, and its membership function is the characteristic function. So we define here a fuzzy number. So is a fuzzy set defined on R, and its membership function satisfies the following properties. Is normal, is fuzzy convex, upper semi-continuous, and the support is compact. And we define here the following classical sets called alpha cats or alpha levels for a fuzzy number U. So a fuzzy number can be defined by any pair U minus U plus, where U minus and U plus, there are two functions defined on 0, 1 a value into R, and satisfy the following properties. And we denote by E1 the space of all fuzzy numbers. We define here the following metric, or the distance between two fuzzy numbers U and V. So it's defined by the following expression. This is the Hausdorff metric, and with this metric E1 is a complete metric space. We define here a fuzzy or a triangular fuzzy number. So it's a fuzzy set. Its membership function is defined as follows, and will be denoted by A, U, and V. So it's easy to prove that the alpha cats of a triangular fuzzy numbers are given by the following intervals. We recall here differentiability of a fuzzy map. So if we take F defined on AB a value into A1, we say that F is differentiable in the first form if it satisfies the following property, and we say F is differentiable in the second form if it satisfies the second property. So we have this result. So if we take a fuzzy map and we define here its alpha cat, so if F is differentiable in the first form, we have this property, and if it's differentiable in the second form, we get this one. Now we move on to the crisp model. For that, we consider the following parameters. So we give here the graphical solutions of the crisp model. So it's clear that number of potential smokers and the number of occasional smokers and temporary quitters, also the number of permanent quitters increase over time, and on the other hand the number of heavy smokers decrease with time. So now we'll move on to the fuzzy model. When we do statistics, we focus on a sample, then we generalize the characteristic study over entire population, and here we have the fuzzy term. So it's reasonable to characteristic, or it's reasonable to model all parameters by a fuzzy numbers, and we have a new version of the previous problem, and we have to resolve the following system of nonlinear fuzzy differential equations where the initial conditions are fuzzy numbers. And we define the following alpha cats. So P, L, S, Q, and R can be differentiable in the first form or in the second form. So we discuss all cases. Here we focus just on two situations, if they are differentiable in the first form or in the second form. And the other cases, they are similar to one of the following two cases. So if they are differentiable in the first form, problem 2 leads up to have the following system of nonlinear differential equation. And if they are differentiable in the second form, we have to solve this system. So we consider the following parameters. We suppose that P0 is around 0.60301, L0 is around 0.24, S0 is around 0.10628, and so on for the other parameters. So these parameters can be mathematically modeled by the following fuzzy triangular number. And it's easy to prove that the following alpha cats or its alpha cats are defined by the following intervals. So we give here the following, we give in the following figures the graphical solutions of problem 1. If they are differentiable in the first form, so we can say that this is the graph of potential smokers, this is the crisp solution, and this is the fuzzy solution for alpha equal to 0. This is the left and right branches of the variable P, potential smokers. This is the graph of occasional smokers, this one for heavy smokers, temporary quitters, and permanent quitters. So if we analyze these figures, we can see that the graphical solutions are incompatible with biological facts. Now we'll move on to the second case. If they are differentiable in the second form, the graphical solutions are given in the following figures. So we can say here all cases, the graphical solutions are biologically meaningful and coherent with the crisp solution. So in the next, we focus just on the situation where P, L, S, Q, and R are differentiable in the second form, and we give here the fuzzy solution for all cases alpha n 1. And we have here the graphical solution of potential smokers, and the graphical solution for occasional smokers, heavy smokers. This is for temporary quitters, and the last one for permanent quitters. So if we analyze these figures, for example, this one, so for alpha equal to 0, we have, this is the crisp solution, this is the fuzzy solution for alpha equal to 0, and we have the crisp solution is limited by the left and right branches of the variable P, and in this case we have as a band of solutions, this is all possible cases of potential smokers. And if alpha equal to 1, we are in this case, the projection of the peaks of the triangles coincide with crisp solution. So which means that for alpha equal to 1, we are in the classical situation, and when alpha equal to 0, we have the support of potential smokers, and so on for the other parameters. Last section is a conclusion. So the main difference between the classical model and the fuzzy model, that the fuzzy model exploits parameter uncertainty, whereas the classical model doesn't. In a sense, the classical model is a particular instance of fuzzy model. I would say that when alpha equal to 1, we are in the classical situation. So the classical model is a particular case of the fuzzy model. And in addition, we saw that crisp model is derived from a best feed to data, while the fuzzy model is constructed from biological principles. In other words, the fuzzy model provides a clear and meaningful characterization of parameters. And the last part is some references used in this paper. And thanks for your attention.
Thank you very much. You have the first, you have respected the time. If you have some question, if somebody have a question. Anybody have question? Thank you very much. We end this session. Thank you.
Hello. Hello.
Hello.
There's still one presentation. It's for me. Hello.
We have in our agenda.
It's updated. It's updated. I think.
Don't have in my program. I don't have presentation. But
this session is MM2.
Yes.
I will see with if you have a presentation, you can teach it.
Sorry.
You can do it.
Thank you.
But I don't have in my program in my agenda. I don't have
it. It was planned for tomorrow, but I asked the organizer committee to change my timing, and they update it, and they have here the PDF of the program. I don't know if you have the updated program.
You can give us.
Okay, thank you. So I will share my screen. The presentation, do you see the presentation? Hello?
Yes. We don't hear you.
Do you see the presentation?
Yes.
Thank you.
You can begin.
Hello everyone. I'm going to present some conclusions of path analysis. The conclusion of the correlation matrix applied by our path model. First of all, I would like to take the opportunity to wish to all of you a great quarantine.
Please, I want, please, Mr. Belaid. Mr. Belaid, I interrupt. Mr. Belaid.
Yes.
If we can only know her name, his name. Could you, because we have many other, could you introduce yourself, please?
Okay, I'm Marius. I am a student at the Ibn Tufayl University, and I have my presentation. Mbark.
Okay.
Yes, sir.
You can delete.
Okay, shall I begin?
Yes.
Thank you. So I would like to thank ICOA2020 for this event, and I would like to thank my co-workers, namely Amal Hmimou, and my supervisors Zohar Hadri and Yusri El-Kittani. So I'm going to introduce path analysis. This is I'm going to be quick because I think you didn't the presentation. So path analysis has aimed to estimate the model parameters between several variables. The question here is how to estimate these parameters. In classical regression model, we use the ordinary least square, but here we have many equations and many parameters. So, and we have to estimate them simultaneously. This is the path diagram, which is a pictorial representation of a path analysis model. These are a path model have many types of variables. There are exogenous variables. There are variables. For example, because model, there are the disturbances or error terms. This path diagram can be written in a algebraic manner with these equations. For example, we can see that eta1 equals a xc1 plus b xc2 plus zeta1, and so on for the other homogeneous variables. The number of equations is the number of homogeneous variables. We can also write these equations in the compact form like this, with the B is the matrix of, and the gamma are the matrices of the model parameters.